So now that we understand that reactions will occur at certain speeds or at certain rates, let's start looking, at least from a qualitative level, just from the big picture level, what are some of the factors that affect the rate of a reaction? In other words, just because a reaction occurs at a certain speed, does that mean that there's nothing we can do to, let's say, for example, speed it up? Can we do things possibly to slow a reaction down? Right? And so in this episode, we're going to be looking at broadly the four major things that will affect the rate of a reaction. And we will subsequently, in following episodes, start to tackle and basically peel the layers off of each and every one of those factors. So we're going to begin with the first one, which is concentration of reactants. Now, based on everything we've talked about thus far, this one should not be very surprising to you because, as we stated, the more reactants there are, the greater the likelihood is going to be that reactant A is going to find reactant B, right? So this is a good thing if you have a large amount of reactants. And what we find is that as those concentrations go down, then it's harder for reactant A to find reactant B. And the harder it is, then tick, 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 the longer it's going to take. Now, notice I didn't say moles of reactant. We talk about it in terms of concentration. Because if I took, let's say, 10 particles of A and 10 particles of B, which is a teeny tiny amount, but I put them into a very small container, right? Then chances are A and B might quickly find each other. If I take those same 10 particles of A and 10 particles of B and I now put them into a large stadium-sized container, well, we're going to be there forever waiting for A to find B. So concentration of reactants, we'll speak more into this, but that's one that you should already be able to look at and be like, makes sense, right? The second one is going to be temperature of a reaction. Now, in order to understand this one, we're going to go way back, right? And we're going to remember and pull up the idea of the kinetic molecular theory of matter. The kinetic molecular theory of matter stated that all matter was constantly in motion, and the amount of motion had to do with, in essence, the amount of energy that that substance had, or the average kinetic energy, the temperature of the surroundings. So when we talk about the temperature of reaction, if you increase the temperature, then that means that the particles go from moving slowly to a lot faster. And if particles are moving faster, then that means there is a greater likelihood that they're going to bump into one another, which is good, because if particles are bumping into one another, then chances are better that they will react. So at high temperatures, all reactions occur faster. At lower temperatures, the reactions are going to slow down. The third one is a new term that is specific for this unit of kinetics. It's known as the presence of a catalyst. Now, a catalyst, and again, we'll speak more into this in later episodes, but a catalyst, in essence, is a substance, sometimes even maybe a material or a surface, but it's basically a substance that will provide an alternative pathway that a reaction can take. What do I mean by that? Because that was a lot of stuff that I just said there. Well, if normally we have molecule A and it has to find molecule B, right? And we were to leave these two to their own devices floating around randomly in space, this might take a while. But if, let's say, I introduced, let's say, a catalytic surface, literally something as simple as a surface that would act like a wall where if A hits it, it'll get stuck there for a moment. Well, if A hits here and a split second B hits there, now it's possible that A can find B a lot faster. So again, it's not that the catalyst necessarily did anything, but it provided an alternative pathway that the reaction now doesn't have to, for lack of a better word, work as hard in order for reactants to find each other. We will break that down further later on. But for now, just be aware, catalysts speed up a reaction, by providing alternative pathways for the reaction to take. And again, we'll go into more detail. And now, this last one is probably by far the funkiest of all of them. Because to me, when I hear this idea of the reactivity of reactants, what does reactivity, quote unquote, mean anyway? And so to help you with this, the best way I can describe it is that for reasons that we'll get into later on, certain substances are going to better be able to interact than others. So what might lead to this reactivity of a reactant? Well, for example, what state of matter is the reactant in? If, let's say, the reactant is a solid, then that means, thunk, my reactant is going to be on the floor. If I'm passing a gas over that solid, then I have to hope that some of the gas particles happen to pass over the solid at the right moment in order for a reaction to occur. That's not the most efficient of methods, right? That's not the best thing I could do to support the reaction along. So maybe instead of having it react as a solid and a gas, maybe if they were both gaseous, the reaction would occur a lot quicker because now the particles can meet one another more readily or easier or faster, whatever you want to use. So that's one possibility. Another possibility is maybe I have a molecule that's really big and bulky, and the only way that it'll react is that another molecule has to come and interact with it from a certain angle, under a certain direction, under a certain speed, on Tuesdays after 5 o'clock, right? And the more variables you list, right, the more challenging it gets for a substance to react, then that's going to cause my reaction to slow down a lot. So the structure of molecules can fit into reactivity, right? Something else that might play a role is that in the process, if let's say we have to break bonds, let's say we're doing some type of decomposition, and so we're going to break a bunch of these bonds. Well, what type of bonds did we have? Oh, it was a bunch of double and triple bonds. Man, that sounds like it's going to require a lot of work. Yeah, well, if it takes a lot of work to break those bonds, then tick, 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 that might be a really challenging thing to do. So when I throw things like, structures within molecules, states of matter, what the molecule itself even looks like, that's a really big catch-all that I'm introducing. And so I'm going to refer to that very broadly as the reactivity. And for now, all you have to be aware of is that the more reactive the reactant is, I know. How about this? The more readily the reactant will react, then the faster the reaction will occur. The more challenging it is for the reactant to react, the slower the reaction is going to occur. Simple as that. And the irony is that we're going to, like I said, we're going to look at each of these one at a time, but we're actually going to start off by looking at reactivity of reactants first. We're going to see how that plays into determining the rate law or the rate at which a reaction is occurring. So we take it one step at a time, one tick at a talk, and you'll be there in virtually no time.